Hello everyone and welcome to MES's e-learning channel. In this video tutorial, we will be seeing what are the advantages of self-bias configuration over fixed bias configuration. Both of these biasing configurations are discussed in the previous videos. So if you compare both the configurations, you can see that they are almost same. Only difference is that in self-bias configuration, we have a resistor in the emitter terminal RE. So because of this resistor RE, what are the changes that are taking place? Let's go through it. So basically, biasing is done to get a proper operating point, and operating point should be fixed. So operating point is denoted by Q, and Q point has two coordinates. They are IC and VCE. We will write a Q over here since it is related to the Q point or to the operating point. Here IC is nothing but the output current and VCE is nothing but the output voltage. Now if you remember the analysis that we carried out for both the configurations, self-bias as well as fixed bias, we found out two parameters. One was IC and second one was VCE. So we found out IC and VCE. So basically these are the two coordinates and they should be fixed so that Q point is fixed. So these parameters can change because of two major reasons. Basically IC changes because of two changes, one being change in temperature and second is change in value of beta. Beta is the amplification factor. So if these two parameters change, automatically IC changes, and if IC changes, the value of IC changes, automatically Q point changes because IC is one of the coordinates of Q point or operating point. So let's see if RE is considered in self-bias, what is the advantage of it? So how temperature causes change in IC? Now if you see, IC is equal to beta IB plus beta plus 1 ICBO. We already know this, and this is nothing but reverse saturation current, and this is nothing but leakage current. So this is leakage current. ICBO is nothing but leakage current. So if temperature increases, the minority charge carriers increase, and because of that the leakage current starts increasing. So if leakage current, which is ICBO, increases, it will increase the value of IC, right? So if temperature increases, ICBO, which is the leakage current, increases, and it implies that IC, which is the collector current or the output current, that also increases. So we don't want the value of IC to change, but it is changing. So how we can control this? So this thing is controlled in self-bias configuration because of the addition of RE resistor. So if you remember the analysis that we carried out for self-bias configuration, we applied KVL in the input loop, and by applying KVL in the input loop, we got this equation: VCC minus IBRB minus VCE minus IERE equal to 0. So this is the equation that we got by applying KVL to the input loop. Now we know that IE, which is the emitter current, it is equal to IC plus IB This is the collector current and this is the base current. Both of these are incoming currents and this is the outgoing current. So outgoing current is the addition of both of the incoming currents. Now if IB is very less, generally IB is very less, so we can neglect it, and if we neglect it, IE is approximately equal to IC. Okay, so IE is approximately equal to IC. Now if you look at this equation, we have IERE term present. Now if suppose IC increases, okay, if IC increases, this implies that IERE will also increase, right? If IC is changing, this term is also changing because IE is approximately equal to IC. So if IC increases, IERE also starts increasing. Now suppose this is equation 1. From this equation 1, let's take IB or the base current on one side. So we get IB is equal to VCC minus VCE minus IERE upon RB. Now here we can see that IERE is increasing, right? So if IC increases, this term IERE also increases. Now if IERE increases, automatically IB will decrease, right? So IB is decreasing when IERE starts increasing, and we know that IC is equal to beta IB. So if IB starts decreasing, automatically IC will also start decreasing. So even if there is a rise in temperature because of this resistor RE, we can see IB is decreasing, and because IB is decreasing, we can see IC is automatically decreasing and it is maintained. So IC is maintained because of RE resistor, which is present in self-bias configuration. The second parameter that changes the value of IC is change in beta. Beta is the amplification factor. So if beta changes, automatically IC starts changing, and if IC changes, the value of Q point changes. Now how the change in beta causes change in IC? Because we know that IC is equal to beta IB, right? So if IC is equal to beta IB, if beta changes, automatically IC changes. So by the addition of this resistor RE in self-bias configuration, the value of IC is maintained. So we have seen that we got IC is equal to this term over here in the analysis that we carried out for self-bias configuration. If you have missed it, you can go back and you can check that out. So let's see how RE maintains the value of IC. So this is the equation of IC that we have, and also we know that beta plus 1 is approximately equal to beta. Now if suppose beta is 100 and beta plus 1 is obviously 101, right? If beta is 100, so 101 is approximately equal to 100. So let's substitute beta plus 1 in this equation as beta. So we get IC is equal to beta into VCC minus VCE upon RB plus beta RE. Okay, so this is the equation that we get, and if we have an arrangement where beta RE is very greater than the resistor RB, then again we can neglect this parameter or this value of RB from this equation. If beta RE is very greater than RB. If this is the case, we can write IC is equal to beta into VCC minus VCE upon beta RE. So here we can cancel out this beta and this beta, and then we get VCC minus VCE upon RE, which is equal to IC. Now we can see that IC is equal to this term over here, and this is independent of the value of beta. We can see there is no beta present over here. So we can see just because of the presence of RE, this term beta RE has gone away, beta and beta has gone, and we can see the final equation is independent of the beta term. So this is how the addition of this resistor RE in self-bias configuration maintains the value of IC, and because of that the Q point or the operating point is maintained. So these are the two advantages of self-bias configuration over fixed bias configuration. But there is a disadvantage over here. We can see that to neglect or to cancel out beta, we had to make sure that beta RE is very greater than RB. Now beta is amplification factor of BJT, and for different BJTs or different transistors the value of beta is different, and it is very difficult to make the value of this resistor RE very much greater than RB so that RB can be neglected. So this is a difficult thing, and this is one of the disadvantages of self-bias configuration. So this is it for this video. Thank you for watching.